Hello class. So today in Zoom we should be going over the angle and magnitude criterion. But just to summarize what we do in Zoom today, I want to go over it one more time. So when we're using a root locus plot, we can use these criterion to 1, determine if a point is on the root locus, and 2, if it's not, figure out how we could put on the root locus. So first we'll start off with our angle criterion. And from a root locus, we had that 1 plus k open loop system transfer function, G O of S, 1 plus k times our open loop transfer function is equal to 0. So this is our characteristic equation, which if you remember, we get from having some open loop system times controller. And if we have a feedback loop with that negative feedback, then our overall transfer function should be k G O of S divided by 1 plus k G O of S is equal to 0, the solutions of which are the poles of our system. So by that rationale, we should have that k G O of S is equal to -1, which we can visualize on our real imaginary plane as an arrow pointing to -1. Where it is 1 in terms of its length and 180 in terms of the angle. So we can say that the angle of KGO of S will be equal to 180. And because we don't really care if, we just care that where our arrow is pointing at the end. So from our point of view, we have the same answer if we go around a couple circles, if we go to 180 in the negative direction. All of those resolve in a vector going to -1. So we're going to specify that any angle that matches that final destination is fine by saying 2n plus 1. And I should have said 180 degrees. Let's put a little degree sign in there, where n is any integer. Because what that tells us is that if we have any number of circles, we'll still be going to the correct area. So now let's go through and see what this looks like when we have a target location. Let's say that we have a couple of poles and zeros. We're going to start off with having our open loop system, GO of S, is going to equal some pole and some zeros and 3 poles. So if we draw these poles, we're going to have them located at, we'll say that there's two complex conjugate poles, 1, 0, and another pole way out here. And our desired closed loop pole is going to be located, and this is just for the purpose of illustration, so we're just going to draw a point. So when we want to figure out a desired pole location, this is a third order system, which means that even with if we just have a proportional controller, we're going to end up with a third order system. However, until we know, we can only look at one pole at a time. So if we have a complex pole here, we know that there would be an equal and opposite pole below, but we're only going to look at the location of one pole when we do root locus, if we're trying to check with the magnitude criterion. So what the angle criterion tells us is that the angle of KGO of S is equal to 180. And the way that we calculate the angle is we're going to start drawing vectors that go from our pole locations. And I'm going to do from our poles going this way. So here we'll have some theta 1. We're going to have it starting at our other pole, going to our desired pole location. This will be theta 2. We always measure from the horizontal. And here we have theta 3. If we measure from our 0, take an angle, measure to that point, and this will be phi1. So with our angle magnitude criterion, what that tells us is that the summation of our vector of the angles caused by drawing from our 0 to our target pole location minus the sum of our, and these should be i's because it'll be as we go from I equals 1 to n, where n is the number of poles, or I equals 1 to m, where m is the number of zeros. Then we take those 0 angles, subtract our pole angles, and if the resultant number is equal to 180 degrees times 2n plus 1, so any number of circles, n can be any integer. Oh, I used n twice there, so let's go ahead and just call this, instead of n, we'll call it p. That's terrible because that's poles. Let's erase that one more time, come up with a better letter. You'd think coming up with a letter would be easier. We'll call it w, opposite of m. So then we have that this n is any number of integers. So it could be 0, it could be -1, it could be 50, either one's fine. But if we get an answer like that, what it tells us is that our desired pole location that we've marked here is possible to have on the root locus. So now we have a point that's on the root locus. Next class we're going to talk about what happens if it's not on the root locus, how we can cause it to be on the root locus. But if it's not on the root locus, we can have our magnitude criterion. And what our magnitude criterion, the way that we'll have that is we now take the length of these vectors. So we'll call this length 1, length 2, and length 3. And we'll have this be length 1 but in purple. So we could call it length phi, just to make it easier to visualize. And our magnitude criterion comes from the magnitude, where we say that k GO of s, the magnitude of that is equal to 1, since the magnitude of -1 is 1. And that tells us that k is equal to 1 over the magnitude of GO of s. And so that magnitude of GO of s is going to be equal to, if we have, let's have GO of s, and I had s plus z, s plus p1, s plus p2. We're going to make that a times s plus z, just so we could see what happens if we have a amplitude in the top there. So, for example, if we had that this was 3s plus 7, s plus, and that looks like a set, let's say -10, and here we have s squared plus 3s plus 58. I don't know, that looks underdamped to me. Then our a value would be 3. So if we have that all of the terms in front of our s are 1, and we just take that amplification out, that would be our a for this example. Okay, I ran out of space, so just moved everything that you should have on your paper up. So we have that GO of s is equal to a over a times s plus z1 times s plus z2 times s plus z3, however many of z's we have. So we could see z1, z2, and so on. Doesn't matter to us. We have that k is equal to 1 over the magnitude of GO of s, and we can say that the magnitude of GO of s would be equal to a times the product of our 0 vector lengths. So in this case, in that little example we've got drawn up there, we have 1, 0, and the 0 vector has a length of L phi. And then we're going to divide that by the product of our pole vector lengths. So if we wanted for this example, we would say that G of S would be equal to A times, and here we had the length of phi divided by the product of our pole vector lengths, which would be L1 times L2 times L3. And since K is inversely related with our magnitude of G of S, then that would be that 1 over K would be equal to the magnitude of G of S, so K would be equal to the inverse. So the product of our pole vector lengths divided by A times the product of our 0 vector lengths. And in this example, that would be L phi times A, and we would have a L1 times L2 times L3. So if you're having a hard time with MATLAB getting to work, you can find if a point is on the root locus, and you can find your K value even without using MATLAB. So that is our angle and magnitude criterion quickly summed up.